So in lesson 6, we're going to compare polynomial functions. So I'm going to give you two functions. They may be equations, they can be graphs, they can be tables. There's a whole lot of different things it can be. And I'm going to give you something to compare them against. So we have an example here. It's the worked example. We have two polynomial functions, f of x and g of x. So we want to look for the names, right? Here's f of x, and right over here is g of x. And it says, which polynomial has the greater number of real zeros? Okay, so real zeros are those zeros that you can find on the x-axis. It's your x-intercepts. But we also want to make sure that we're dealing with multiplicity. Okay, so be careful with that part of it. So there's a little explanation down here. It says the fundamental theorem of algebra states that the number of zeros must be equal to the degree of the function. So therefore, f of x has 3 zeros. So if we come up here to f of x, right, here's our little degree. So this would be, when we multiply this out, you would have x cubed. So that is a third degree function. So that means it has 3 zeros. Okay. And so then if we look at g of x shows each zero has multiplicity of 2. Now you might be looking to go, how do I know it has multiplicity of 2? Well, I'm going to zoom in on the graph here. Because this graph at this point doesn't just go through -2, it bounces off. This is actually using this -2 as a root 2 times. Same thing over here with 1. So this is used 2 times for a root. So therefore you've got 2 here, 2 roots here. That's a total of 4. Okay, so this is actually a 4th degree polynomial. All right, and so it says which polynomial has the greater number of real zeros. So g of x has the greater number of real zeros, and so that's what you want to make sure that you circle up or identify in some way, shape, or form. All right, so that's the worked example. Let's get into some examples that we're going to work out. All right. So problem number 1, which function has a greater average rate of change for the interval -4 to 4? So problem number 1, I have a graph. I have a graph for f of x, and I have an equation here for g of x. So let's take a look at the function here, this f of x graph. And I want to look and see, all right, so -4 is right here on the x-axis, +4 is right here. And if I go up to the curve, I'm at this point right here. And if I go up to the curve, I'm at that point right there. So my two ordered pairs, all right, I'm just going to work off to the side here. So my two ordered pairs here would be -4, 4, and +4, 4. Okay, so slope says we're going to take our y value, subtract our other y value, then take x divided by x. So we've got 4 minus 4 over 4 minus -4. Lots of 4's in this problem, so just be really careful. 4 minus 4 is 0. 4 minus -4 is 8. 0 divided by 8 is 0. So I now know f of x has an average rate of change of 0 for this interval. And if we look at it, we could basically connect the dots here. And this line that we draw is completely flat. It's not increasing or decreasing, it's just straight. Or it's a flat horizontal line there. All right, so for g of x now, I want to find those same things. I want to find those ordered pairs that I know -4 and +4. I don't know the rest of it. So let's see. I've got Desmos relatively handy here. So I'm going to go ahead and open up Desmos. What on earth just happened there? Okay, that was weird. Okay, much better. Sorry about that. All right, so I had a bunch of stuff in Desmos already. I'm going to go ahead and clear all of this out and just get a fresh start here with Desmos. So I'm going to put in this equation into Desmos. I don't really care what the equation looks like per se, but I can use the table that Desmos will give me to find very specific x values. So 0.5. I'm taking my time here because I unfortunately know all too often that I screw up my equations, when I put them in, I just lose values. So, all right, 0.2 x minus 0.0, all right, times another x. All right, we're good. Now, again, I could look at the table, I could look at the equation over here. It's not terribly helpful though. So instead what I'm going to do is look for a table of values so that I can find these pieces of information. So I'm going to hit the little gear up here. And one of the things I can do is turn this into a table. So I'm just going to select table. And now, obviously, if I look at this table, it goes from -2, -1, 0, 1, 2. I don't have -4 or 4. A couple things you could do. If you notice how -2 right now is highlighted, I could actually just immediately start writing -4. And now it's going to tell me that that's 3.6. So in Notability, I'm going to go ahead and mark that as 3.6. Or the other option you can do is down here, there's a little blank spot. If you tap in the x value of the blank spot, you can just type in the next value. I'm looking for 4, so that's going to be 2.8. And now I'm just going to slide Desmos over just a little bit. All right, I will use it as a calculator in just a second. So now I want to do y value minus y value over x value minus x value. Be careful with those double negatives. All right, so 2.8, no, not 28, 2.8. See, make mistakes all the time. Minus 3.6. That's negative 0.8. And 4 minus -4 is 8. So I'm going to take my answer here. And it's going to be, let's see, negative 0.8 divided by 8. So I get an answer of negative 0.1. All right, I'm going to go ahead and clear out Desmos here. Okay, so which function has a greater average rate of change? Now, you might be looking to say, well, 0 is larger than any negative number. You are correct, but we're talking about a rate of change. And so what we want to make sure that we're dealing with here is which change is greater. It doesn't matter if it's positive or negative, just which change is greater. In example f of x here, there is no change. And in g of x, there is change. So this is actually the greater average rate of change. Even though it's negative, that's okay. So I'm just going to go ahead and circle that up and say g of x has the greater average rate of change. All right, I'm going to slide on down to the next equation here, next little problem. Which function has a greater degree? All right, so we have in the first little box here, h of x has 1 absolute maximum and 1 relative maximum. So let me take a look and see. So let's make a relative maximum here and then a absolute maximum there. All right, so this is at least a 4th degree polynomial. All right, so at least 4th degree. Now, if I look at j of x here, and I look across here, okay, this is going to turn into x squared if I multiply it out. This is x squared right here. This is x to the first. So j of x here, this is only a 2nd degree polynomial. So which function has a greater degree? Well, the one that's at least 4th degree would be greater than 2nd. All right, so circle it up. The work that you show me here will count for these problems. All right, problem number 3, we're back to average rate of change here, but we've kind of changed up what we're giving. So there's no equation here. So in this first one, we have j of x, and I believe that's k of x over here. So for j of x, we're going to look for where is x -1 and where is x +1. So let's see, here's -1, here's +1. So off to the side, I can do my little slope formula here. So I'm going to take y minus y over x minus x. So 0 over 2. So, all right. So j of x has a slope of 0. That's okay. It happens. Now let's take a look at k of x for the graph. All right. And I'm at -1 all the way up here is +3. And what was my other value? Oh, 1. Oops. And I'm down here. Okay. So we've got -1, +3, and +1, -3. So a little slope intercept or slope equation here. So I'm going to do -3 minus 3, and then 1 minus -1. So that's going to be -6/2, which is equal to -3. So again, we just talked about this, I don't know, 2 examples ago. If we're looking at change and we want to see which is the better change or which is the greater change. Well, this one didn't change at all, and this one changed by 3. Now, yes, I know it's negative, but that's still change. And changing by 3, even if it's a decrease, is still a greater change than not changing at all. All right, so it's a little bit weird, but k of x is going to be the one that has the greater average rate of change for that problem. All right, problem number 4. We're mixing and matching a lot of ideas here. So problem number 4, we have the basic quadratic function. So if I were to graph this, it would look just like that-ish. All right. Then we've got g of x, which references, right, this is our basic quadratic function, but now we've shifted it. All right. So we've shifted this, what would this be? Right 2 and then up 1. So if I were to go, and I'm actually going to put this on the same exact graph. So instead of hitting this right here at the origin, I'm going to shift over 2 and up 1 because I just want to get a feel for what this graph looks like. So something like that. Okay. And it asks which function has a greater output for a given input. Now, output are your function values, your y values. Your input are your x values. So if I go here and I say, okay, let me put in 0 for x. Well, it looks like that blue graph, right, the g of x graph, is greater than the f of x. Well, that's cool, but unfortunately, that's not true over here. So if I were to put in, let's say, 5, then the red curve is higher up than the blue curve is. So that means it has a greater function value, greater output. So unfortunately for problem number 4, you don't know. So this cannot be determined. All right. So unless I gave you a specific function value, you're not going to be able to figure this one out across the whole thing. Okay. All right, problem number 5. Which function has a degree that is divisible by 2? Well, if we're asking for something that's divisible by 2, I want an even degree function. Okay. Now, this is going to be a little bit weird because I don't see any real function equations. I can't see a picture here. What I can see, though, I've got p of x, and if I look at my outputs here, my y values, so this is 2, 4, 6, 8, 10. This is increasing by a steady amount each time. So if I were to graph this, what would end up happening is I would actually be graphing, let's see, some form of a straight line. Okay, just a quick little sketch here. So this has a straight line, which means this is degree 1. So yeah, degree 1, not so much divisible by 2. But it says the function q of x has only imaginary zeros. Now what you need to know is imaginary zeros come in pairs. So anytime you have a function, if you know that one of your roots is imaginary, there has to be a second imaginary root as well. So you could have 2 imaginary roots, you could have 4 imaginary roots, you could have 8 imaginary roots, you could have 800 imaginary roots, but they have to come in pairs. And if you only have imaginary roots and they only come in pairs, then whatever you have, you're dealing with an even power, all right? So whether your power is 2, 4, 6, 8, 312, it's an even value, all right? Okay. So problem number 6 here, example 6, determine which function has the greater output as x approaches infinity. So this would actually be working really well with our end behavior. So what we're looking for is as x approaches infinity, what is happening to our function? And one of the best ways to deal with this is to graph it, okay? So we've got r of x here. We know r of x is an odd function, but I'm telling you that a is less than 0. So that means I'm going to take my normal, and I'll put this in an orange highlighter here. The normal odd function looks something like that. However, since our a value is negative, right, it's less than 0, that means we're going to have some kind of a reflection over the x-axis. I'm going to go ahead and take out that original one. So for this one, as x approaches infinity, r of x is approaching negative infinity, right? It is dropping here. That's decreasing. Okay, k of x, we have an equation here. Our highest degree is a power of 6, and it is a positive x to the 6. So if I graph this, we've got some kind of positive value. There could be a lot of little mountains and valleys in the middle there, but remember we're looking at the infinity part of this. So as x approaches infinity, k of x is also approaching infinity. So greater output is going to be the positive value of infinity as opposed to the negative infinity over here. So that means k of x has the greater output. All right, keep going. We're just going to keep rolling on through these examples here. Problem number 7, determine which function has the greater output as x approaches negative infinity. Okay, so I'm going to do the exact same thing I did in the last one. Let's see, we've got x to the 8th here, but there's a negative in front. So that means it's an even degree function, but it's been reflected. So it's going to look something like this. So this is going to be as x approaches negative infinity, t of x approaches negative infinity. Okay, right? This graph is dropping over here. Now, part 2 here, we have a quartic function. This is a degree 4 with y-intercept 0, -5, and all imaginary roots. Okay, so imaginary roots, we just talked about this. There's 4 imaginary roots here, and what this tells me is, all right, so let me get that 0, 5 here. I can't cross the x-axis, because if I cross the x-axis, then I wouldn't have imaginary roots, I'd have real roots. So this is going to look something, you know, again, mountains and valleys in the middle there, but it's going to look something like this without ever touching the x-axis. So if I look at this, as x approaches negative infinity, what is this? S of x is approaching positive infinity. It's a horrible infinity sign. Okay. So which one has the greater output? Well, positive infinity is going to be the greater number to negative infinity. So that's going to give me S of x has the greater output. All right, so this one's already been worked out for us. We've got Sam here and we've got Otis. They compared these two functions to determine which one has an odd degree. Okay, so, and I'm not going to even read their answers yet. I'm going to go in and do this like I needed to do this. So f of x has an absolute maximum value. If you have an absolute maximum, you have a graph that looks something maybe like this, where this point up here is your absolute highest point you ever hit, okay? Now, if you have an absolute maximum, you don't have an odd degree. This has got to be some kind of an even degree function, okay? So this is even degree. If you notice, the end behaviors match here. So that's, again, another way I know it's even degree. Now, if I look at g of x, I don't want to multiply this whole thing out. I'm going to make mistakes. I don't want to deal with it. All I'm going to multiply is I want to see what happens if I take my x terms and I multiply them together to figure out what my leading term would be. So if I take x to the fourth times negative x, that's negative x to the fifth, times 2x cubed would be negative 10x, or that was 2x squared. So that would be negative 2x to the seventh so far, times x to the fourth, so negative 2x to the 11th. Let me double check that. 4, 5, 6, 7. Yes, so this is going to be, when I multiply it out, negative 2x to the 11th. I know there's other stuff attached to that. I am not worried about any of it. But if this is the number 11, that tells me that this g of x function right here has the odd degree. So now let's take a look at what Sam said. The function f of x has an odd degree because odd functions approach positive infinity as x either increases or decreases. This means that f of x has a maximum value. No, Sam, it doesn't. All right. So, yes, you can approach infinity, but approaching infinity has nothing to do with a maximum value. So be careful about those. Let's see what Otis had to say. The function g of x has an odd degree. When I multiply the factors, I got the term with a highest exponent of 11. That's exactly what I did. Therefore, g of x is odd. So who is correct? Let me give a quick writing here. So this is Otis is correct. And when it says justify your reasoning, excuse me, you can either write it out in a sentence form like Otis did, or you can kind of show your work to justify. Either one is okay. All right. I think this is the last one. It is the last one for this video. I will do the second part of this, or the last couple of examples in a separate video. All right. Isaac and Tina disagree over which function has a greater y-intercept. So let's find the y-intercept. For g of x, I'm going to find the y-intercept. I'm going to use Desmos. I'm going to pop it back up. I'm going to take advantage of that technology that I've got. Let me take a quick minute here and get rid of the stuff that was there. All right, so I've got y equals 2 times x minus 2, x plus 2. Helps if I actually register the 2. And then x minus 3. And then at the very end, there's a minus 4. All right, I'm going to zoom in as best I can here to get towards the origin. The nice part is I don't ask for an equation here or a sketch. All right. So I want to highlight the line, and you're going to see all of these little gray points up here. Each one of these gray points represents some critical piece of information. So the three of them right here would be your x-intercepts. You've got a relative minimum. All the way at the top here, you've got a relative maximum. And then right here, where this green curve crosses the y-axis, is the y-intercept. So that's the point 0, 20. Okay, I'm going to go ahead and get rid of Desmos because I don't need it anymore. And then for h of x, I have a table of values, and I'm going to look for where is x equal to 0, and it's right here. So my table of values says I have the ordered pair 0, 4. So if I compare a y-intercept of 20 compared to a y-intercept of 4, the 20 is the greater y-intercept. Okay, so let's see who's correct. So Isaac says the function g of x has a greater y-intercept. I calculate the y-intercept by substituting 0 for x. This value is greater than 0, 4, shown in the table. So Isaac is absolutely correct. Tina, the y-intercept of h of x is 0, 4, and the y-intercept g of x is 0, negative 4. Tina made a common mistake. Oftentimes after we've shown you guys standard form for quadratics, a lot of students say, oh, whatever this last number is, this has to be the y-intercept, and that's just not true. To find the y-intercept, you can use the technology like I did, or replace all of these x's with zeros, and then figure out what happens when you multiply it out. And in this case, you get 20, not negative 4. So Isaac is correct here. Let's go ahead and mark Isaac as being correct. Isaac is correct. Okay. So that was a lot of comparing functions. You need to know about extrema, x-intercepts, y-intercepts, degrees, a lot of different pieces of information. So if you have any questions or concerns, please let me know.